Hello, everyone. I'm Xiaoping Du from Indiana University, Purdue University, Indianapolis. Dr. Xinpeng Wei is my former student from Missouri University of Science and Technology. Dr. Daozhu Han is my former colleague from the same university. And today I'm going to report you some of our work about physics-based Gaussian process method for predicting average product lifetime in the design stage. And let me give you some background. As we know, we use predictive models for engineering design, right? So we use models to design components and design systems. In the meantime, we can also use models to bridge design and post-design stages. Okay, if we do this, we can get some optimal pathway to effectively account for future system operations. And we do this in the early design stage. It is very important, okay? One important aspect is to predict the product life early in the design stage. And currently, we could use data-based method, but it might be too late. It might be too late because we need data, right? So we want to do this early in the design stage. So as you can imagine, this is not an easy task here, right? So the objective of this study is to demonstrate the feasibility of doing so by using a physics-based approach. So this is our objective. We develop a physics-based Gaussian process method for predicting mean time to failure, or MTTF, early in the design stage. You may wonder why we need to consider MTTF, because it is an important metric used to estimate the lifespan of products. It is also a major reliability index for many important systems. We can also use it to make a lot of decisions in terms of maintenance, warranty, and also something about lifetime cost analysis, right? But why do we need to do this during this design stage? The huge benefit is that we can directly link design variables to MTTF, right? If the mean time to failure is not good, if it's short, right? So we can change our design variables to improve it, right? So what we can do is to perform what-if analysis, design, exploration, and optimization, because we know the link between design variables and MTTF. We can change our design variables to improve the average lifetime, right? But this is not an easy job, as I said. Why? Because this task involves time-dependent models and also stochastic processes, right? And this job is also computationally expensive because we need to call physical models, computational models, and usually they are very expensive, like CFD models, FEA models, right? So we have big data in the input side, but we have small data in the output. Why? Because it's hard, it's expensive to get the output, to get the responses, okay, to get the performance variables, right? So because of this, traditional statistical methods could not work. For example, we couldn't use Monte Carlo simulation because it needs to call the models many times. So that's the reason we decided to develop some more efficient methods. So let me give you something about our proposed method here, just the basic idea, right? So during design, we use physical models. For example, this model, y is a function of input variables x, and this y or the response also depends on time, right? So the input variables x here may be random variables, there may be stochastic processes, right? Because of this, the response is also a stochastic process. How do we define a failure, right? If y is less than 0, we have a failure, right? If y is less than 0, probably the safety factor is less than 0, so we get a failure, right? Okay, so how do we approach this problem? Of course, we can find the distribution of the time to failure, right? We use tau for the time to failure, and then we find its expectation or its average, right? But this method is very, very expensive, okay? We cannot afford the high computational cost, right? It may take hours, days to get the result, okay? So our method is like this, right? Let me just show you the figure here, right? This curve is the output y with respect to time, right? It's just a sample path of the model. Remember, y is a stochastic process, right? It's random, okay? So the response y changes randomly over time. This is just a sample path here. So you see here, y decreases at the beginning, and then it reaches to 0, and then we get a failure here. But you also see 2 time instants. So 2 time instants, we have downcrossing here. So when y reaches 0, what we need is the first time instant here. We call it the first passage time, right? So what we need is this first passage time, because we have randomness in the input, and this first passage time tau is a random variable. Okay? As I said, it is extremely costly to find the distribution of this tau of x. So our strategy is to generate surrogate model for the response y. So the surrogate model should be much cheaper, right? Much cheaper, okay? So we can generate as many points as we want for the input variables x, because it's cheap, right? Because we know the distributions, we know the processes of x, okay, right? But we cannot generate many training points for the response y. In other words, we cannot get many labels, okay, for the response y. Okay, so that's a reason, okay, we're going to use some machine learning tools to get the surrogate model. And the tool we use for this study is the Gaussian process regression, okay? So we generate Gaussian process model for the original performance function G here, right? And what we do is to use the active learning process, the strategy here, right? Active learning strategy, because we don't want to call this computational model many, many times, right? So at first, we generate the initial Gaussian process model, right? And then we add more training points, but we do this one by one. So each time we just add one more new training point, and then we update the model, and we do this until we get the convergence. So this is the simple flowchart about what we have done, right? So we have 2 steps. In the first step, we use design of the experiments to get some initial points, training points, right? And then we use the initial training points to build the Gaussian process model. Of course, okay, this model is not accurate enough, okay? So in the second stage, okay, once we have the initial model, and we use the model to identify the next training point, right? Next training point, okay? We call the response again, right? So we just add the new point to the training point set. We update the model here, right? So we just repeat this process until we get an accurate model. Okay. After this, we get the model. The model is very cheap to run. It may take seconds or less than 1 second, right? Actually, we do have the third step here. So after we get the model, we can use the model to do anything, including finding the distribution of the first passage time. So that's what we want, right? So this is a very simple flowchart here. And this is the detailed flowchart here. So we do have some equations, mathematics behind this. I'm not going to give you all the details here, but let's just look at one example here. And this is a space 12 system here. We have 52 bars, okay? The computation model is the finite element analysis model, FEA, right? So the model is expensive to run. And this system is subject to some random forces. And some forces are random, actually Gaussian stochastic processes. So this means that they change randomly over time. Okay. We have other random variables like the random material properties. Now, what is the failure mode? Okay. If the deflection of some node is large, we think the system fails, right? So we have this problem here, right? And we use the proposed method to predict the average time to failure. And to verify the result, we also used Monte Carlo simulation. For Monte Carlo simulation, we had 10 million samples, right? So this means that we had to call FEA 10 million times. And for this problem here, the FEA model is relatively inexpensive. Okay, so that's a reason we could call the model 10 million times, right? Just for the demonstration here, right? And now let's see the result. Our method produced this MTTF 4.79 years. Okay, if you look at the Monte Carlo simulation result, it is the accurate result. Okay, the answer is this 4.75. You see, the difference between the two is very small. Okay, so the relative error of the proposed method is only 0.8%. But if you look at the efficiency here, the proposed method just called the FEA 56 times instead of 1 million times, right? So from this example, you see the high efficiency of the proposed method, okay? If you look, read the paper, you're going to see more examples. So finally, so what we found from this study is as follows. It is possible to predict MTTF early in the design stage. Okay. And if the physical models are accurate, if the input variables to the models are accurate, the prediction will also be accurate. But we do have some limitations because in this study, we only consider one failure mode, only one failure mode and some simple systems, okay? So our future work will target multiple failure modes, more complex systems with multiple components and probably repairable systems. So the long-term goal is to predict more operation performance measures, for example, the availability, mean time between failures, and failure mode, right? So the same strategy could be used for the resilience and a robust system design. Okay. Finally, I'd like to thank the support from this NSF grant. Thank you very much for your attention.